All right, so we're in 10.2 now. 10.1, we were looking at parametric equations for curves and just kind of walking through some of the basics of those. What is a parameter interval? How do you sketch a curve from parametric equations? How do you eliminate the parameter? Things like that. At this point, we want to look at how to do calculus with parametric curves. And we're basically going to kind of go back over a lot of the things we've already done in calculus. So for example, finding slopes of tangent lines, areas under curves, arc length, surface area, things like that. But how to perform those tasks when your curve is given to you parametrically instead of just with y as a function of x or x as a function of y. So we're going to start with the topic of tangents. That you spend a lot of time talking about this in Calculus 1. In Calculus 1, we show that if you have some curve given by y equals f of x, if f of x happens to be differentiable, then you can find the slope of a tangent line to any point on that curve by evaluating the derivative, dy dx. So dy dx can be interpreted to mean the slope of a tangent line to a curve. Now, if instead we're given a set of parametric equations like x equals x of t and y equals y of t, let's suppose for a moment that we're able to eliminate the parameter in those parametric equations, which means in this case we can write y as a function of x. Okay, that's what eliminating the parameter would do. Remember, it puts a relationship between the x and the y. Then because x is also a function of t, y of x can be alternatively written as y of x of t. So this is a composite function. And remember, the goal here is to find slopes of tangent lines to this function, which specifically is what dy dx represents. So what I would want to do here is differentiate. I'm going to differentiate both sides with respect to t here. So if I do that, I'm going to get y prime, or I could also think of that as dy dt, y prime. Then on this side, because I'm dealing with a composite function, I would need to use my chain rule. So I would take the derivative of this outside function, y prime, leave the inside alone, x of t, but then take the derivative of the inside and multiply it on the outside, x prime of t. It's better to see what's going on here if we write things in terms of Leibniz notation. So this y prime came from differentiating with respect to t specifically. So I'm looking at dy dt here. Y prime of x in there, I can think of that as dy dx, and then I'm multiplying that by the derivative of x with respect to t, dx dt. Of these three derivatives that are showing up here, only dy dx represents the actual slope of a tangent line. So I'm going to solve this for dy dx. I get dy dx equals dy dt over dx dt. And this is what we use to find slopes of tangent lines to parametric curves. Notice if you were to think of the dy dt and the dx dt as if they were fractions, you could cancel the dt's out here, which would leave me with dy over dx, exactly what I see here. So that's a way of remembering this. In addition to being able to find dy dx from parametric equations, it's also helpful to be able to find the second derivative of y with respect to x. And that's because we use the second derivative in Calculus 1 to get information about a curve, specifically things like concavity and points of inflection, that kind of stuff. So how do you get a second derivative? Well, the second derivative of y with respect to x isn't what you might think it is. It's not the second derivative of y with respect to t over the second derivative of x with respect to t. After seeing this, that's probably what your gut is telling you, and your gut would be wrong in that case. The way that we find the second derivative of y with respect to x is we use this formula, but instead of finding the derivative of y with respect to x, I find the derivative of y prime with respect to x, because that would be the same thing as the second derivative of y. So here, my second derivative of y with respect to x can be thought of as dy prime dx. That y prime there, I can think of as something that I want to substitute for the y's that show up in this equation here. And the only place I see that y is right here on the right-hand side. So that dy prime dx turns into this, dy prime dt over dx dt. Notice there was no place to fit that y prime in here, so my denominator stays the same. But remember, y prime is the same thing as dy dx, and this is telling me to differentiate it with respect to t. So another way of writing that is d dt of dy dx. This thing here is how I find second derivatives of y with respect to x when I have parametric equations. Okay, so there's a few things now that we can do with this information, because there's lots of stuff that you do with derivatives and second derivatives in Calculus 1. So let's take a look at some of that. Here, I want to show that the curve given by this function right here, or this set of parametric equations, x equals cosine of t, y equals sine of t times cosine of t, has two tangent lines at the point 0, 0. And then we want to find both of their equations. This is something that does not happen when you have a curve given by a function. You never get two tangent lines at the same point, but it can happen with parametric functions. And the reason it can happen here, sorry, I said parametric functions, I meant to say parametric equations. If you were to actually graph this thing, you only need to go from 0 to 2 pi to graph it, because the period of both of these functions is 2 pi. So it just ends up retracing that curve if you go beyond that. But the curve ends up looking kind of similar to like a figure 8 with slightly sharper corners, but kind of like that. Okay, so if you notice, it passes through the origin twice as I trace the curve once, because the curve intersects itself at the point 0, 0. As you're going this way, you get a positive slope on your tangent line, but as you're coming this way, you get a negative slope. That's two different tangent lines happening there. So we want to find the equations for both of them. To do that, we're going to find dy dx, which we saw requires us to know dy dt and dx dt. So what is dy dt? Well, dy dt is the derivative of this with respect to t. I would need the product rule. So the derivative of the first times the second would be cosine times cosine, or cosine squared of t. And then the plus the derivative of the second times the first. That's negative sine times sine, or minus sine squared of t. You may remember from from trigonometry that this is one of your double angle formulas for the cosine function. This is the same thing as cosine of 2t, which is a better way to write that. We also need dx dt. Dx dt is easy. It's just the derivative of cosine of t, which is negative sine of t. So that tells me that dy dx, which is the one derivative that actually gives me slope, these things by themselves don't give me slope. We know that this is equal to dy dt over dx dt. That's what we just derived on the previous page. So that would look like negative cosine of 2t. There's my dy dt showing up with the negative coming from here, sine of t. Okay? Now, we have a way of determining slope, but how do I evaluate the slope at this point right here? The point has an x and a y value. What it does not show me is the t that gets me to that point. So I have to figure out for what value or values of t will my parametric equations give me the point 0, 0. Okay, so notice if the x is equal to 0, then I specifically need cosine of t to equal 0, because that's what I'm seeing here. But if cosine of t is equal to 0, then y would also be equal to 0, because it has a cosine of t in here. So 0 times whatever sine of t ends up being will still be 0. So really, I'm just looking for where cosine of t is equal to 0. And like I said before, we only need to look for solutions to this within one revolution of the unit circle, or values between 0 and 2 pi, because if we go beyond that interval, we just keep retracing the same curve. So this has two solutions between 0 and 2 pi. It's equal to 0 at pi over 2 and 3 pi over 2. Those are the two values of t that work. I'm going to plug each of these into my slope here to get those two different slopes. So if I wanted to evaluate dy dx, but for the particular value of my parameter when t is equal to pi over 2, Then I get cosine of 2 times pi over 2. That's cosine of pi, which is -1, times a negative here. That makes a +1. Sine of pi over 2 is also +1. That would just equal 1. Okay? If I do dy dx, but this time evaluate when t is equal to 3 pi over 2. Okay, well, multiplying that by 2 gives me 3 pi, which is coterminal to pi. So my numerator comes out to the same thing, which would be -1. This time, though, sine of t is also -1. So I get -1 over -1, which is 1, but then this negative out here makes that -1. So I have a +1 slope and a -1 slope, both of which share the point 0, 0. So we're looking at a line with a y-intercept of 0 and a slope of 1. That's the line y equals x, and a line of slope 1 still with a y-intercept of 0. -1. That's y equals -x. Those would be the two tangent lines at the origin for this curve. Okay? Cool. So that's one problem down. Let's look at another example where we're still working with some of these, some of the stuff that we already derived. In this case, I want to find all points on this curve that are given by these parametric equations here, at which there are horizontal or vertical tangents. So coming back here, remember, this is the formula that I want to use. dy dx is equal to dy dt over dx dt. We know that we get horizontal tangents when our derivative equals 0, which only happens when dy dt equals 0, provided that dx dt is not also 0. So what I'm going to end up doing is finding dy dt and figuring out when is that equal to 0. That will give me horizontal tangents. Vertical tangents happen when our dy dx is undefined, which specifically happens when we have to divide by 0 somewhere, dividing a non-zero number by 0. So to find vertical tangents, we're looking for where dx dt is equal to 0. That's basically what this amounts to. So going through that process, let's find dx dt. And that's right here. So that's going to be 3t squared minus 3. Okay? Or if you factor, I can pull a 3 out. I'd get t squared minus 1, which factors to t plus 1, t minus 1. Okay? Remember, we want that to be equal to 0 to find vertical tangents, which would only happen if t is equal to plus or minus 1. All right? Now let's check out dy dt. What's going on with dy dt? Well, if I take its derivative, I have t cubed minus 3t squared, so that would be 3t squared minus 6t. If I factor a 3t out, I get 3t times t minus 2. Okay? If I set that equal to 0, I get different solutions. T equals 0 and 2. Okay? So now, to find our vertical and horizontal tangents, or the points at which we get vertical and horizontal tangents, I'm going to say vertical tangents at... It's going to happen when t is equal to plus or minus 1. But neither of those are points. Those are parameter values. So to get the points where these occur, I have to take these parameter values and plug them into my original parametric equations. So let's see. If I plug t equals 1 into these, I'm going to get 1 minus 3, which is -2. That's my x. And if I plug it in here, I'm going to get 1 minus 3 again, which is -2. So that corresponds to when t was equal to 1. I have a vertical tangent at -2, -2. And then if I plug a -1 in, so that's going to give me -1 minus -3, or -1 plus 3, which is 2, for my x. And then if I plug that in here, I'm going to get -1 minus, well, -1 squared is +1 times -3, that would be -3. So -1 minus 3 is -4. These are the 2 points where I'm getting vertical tangents. Horizontal tangents, like we saw, come from when dy dx is equal to 0. So horizontal tangents at what values? Plugging a 0 into both of my parametric equations is going to give me 0 here and 0 there. So I get the origin when I plug t equals 0 in. When I plug a 2 into these parametric equations here, I'm going to get 2 cubed, which is 8, minus 3 times 2, which is 6. So 8 minus 6 is 2. And then when I plug a 2 in here, 2 cubed is 8, minus 3 times 4 is negative 12. So 8 minus 12 would be negative 4. This happens at t equals 2. Now this is interesting because I'm seeing the same point here, right? So you might be asking, how can I get a vertical tangent and a horizontal tangent at the same point? Well, again, remember, you can get two different tangent lines at the same point if the curve intersects itself there. So it might be worth going to a graphing utility like Desmos or something like that that can handle horizontal tangents, and just try seeing what the graph looks like. See if the curve is actually intersecting itself here, and if that intersection looks like it has both a horizontal and vertical tangent. Okay? All right. Here we go. One last problem for this video, and then on the next video we'll move on to a different subject within the calculus of parametric equations. So for this one, I want to use that second derivative that we found. For what values of t is the graph of x equals t squared plus 1, y equals e to the t minus 1 concave up? So we're specifically looking for where the second derivative of y with respect to x is positive. That's where we get concave up. There's some ingredients I need to figure out here. Let's start with dx dt and dy dt. dx dt would be 2t. dy dt would just be e to the t. Okay? Now remember, in our second derivative, which was over here, I needed that dy dx, which we find using this formula here. Then I need to differentiate that with respect to t. So let's find dy dx next. dy dx is the same thing as dy dt over dx dt, or e to the t over 2t. Okay? I take this and I differentiate it with respect to t. That's what showed up in the numerator of my expression for the second derivative of y with respect to x. So I'm differentiating this with respect to t, which requires the quotient rule. So that's going to be 2t e to the t minus e to the t times 2, so 2 e to the t, all over my denominator squared, which is 4t squared. Okay? Now, my second derivative of y with respect to x, remember, is equal to this expression here over my original dx dt. Okay? So I'm going to get 2t e to the t minus 2 e to the t over 4t squared, all divided by 2t. Okay? This denominator I can bring down and simplify. I could do a couple other things as well. I can pull a 2e to the t out of everything, which would leave me with this numerator up here, just t minus 1, over 4t and 2t. When I multiply those, I'm going to get 8t cubed. In fact, I can even do a little bit of cancellation here to get that. Okay? Now, e to the t is always positive. So in order for this thing to be greater than 0, I need that t minus 1 over t cubed to be greater than 0. The way that we do this, if you remember from Calculus 1, is we find the zeros of both your numerator and your denominator, which is going to be, the numerator will be 0 when t is equal to 1. My denominator is only equal to 0 when t is equal to 0. You create a little number line, or at least this is the way I like to do it, and you find those two values, 1 and 0. that takes the number line and splits it up into 3 segments, 3 intervals. I want to pick sample points in each of these intervals and determine which of those sample points are giving me positive values here and which ones are giving me negative values. So for example, if I take a -1, which belongs over here, I have -1 minus 1, which is negative, it's -2, divided by -1 cubed, which is -1, also going to be negative. Negative over negative is positive. E to the t is always positive, so that gives me a positive value. So here we would see that our second derivative, y double prime, is positive. If I pick a sample value in here, say 1/2, 1/2 minus 1 is a negative number, 1/2 cubed is a positive number, negative over positive is negative, times positive is still negative. Y double prime is negative here. Now pick a number greater than 1. Let's pick something ridiculous, like a billion. A billion minus 1, clearly positive. A billion cubed, clearly positive. Positive over positive is positive, times positive, still positive. Y double prime is positive there. Since we want the intervals on which our function is concave up, I would find anywhere my second derivative came out positive and identify those. So we are concave up on these 2 intervals. -infinity to 0, which is what this interval is, and 1 to infinity, which is this interval here. Okay? That finishes that question. We'll move on to the topic of areas under curves in the next video.